Hello. In today's video, we will be covering Chapter 8, Addition Reactions and Alkenes. An alkene is going to be able to undergo an addition reaction, and this is more or less the opposite of an elimination reaction. In this chapter, we're going to add a large number of reactions to our organic chemistry toolbox, and all of these reactions will be addition reactions where we take two atoms or functional groups and add them across a double bond. We're going to be converting a carbon-carbon pi bond into two new carbon sigma bonds with the various different atoms. Depending on what type of reaction we're running, we can kind of gain some information from the name. So for example, if we're adding a hydrogen and a halogen across a double bond, that would be a hydrohalogenation. If we're adding water across a double bond, that would be a hydration reaction, and so on. So a pi bond is going to be an electron paired donor. They can act as a base or as a nucleophile. If they react with an acidic proton to form a new carbon hydrogen sigma bond, then they would be acting as a base, and they can also act as a nucleophile to create a new bond with an electrophile, resulting in a carbocation intermediate. Alkenes are quite prevalent in nature and industry. They're found in many natural products. Here are a few examples of natural products. The small molecule responsible for the odor of garlic contains a disulfide bond. Sulfur is an atom which is notorious for being contained in many smelly molecules, and it also contains two alkenes. There are a large number of other small molecules that contain alkenes. For example, limonene is a molecule that you would extract from an orange, and the estrogen family, the steroid family, including cholesterol, contains different alkenes. Since these functional groups are so reactive, they can be used to easily transform certain molecules to other molecules. In industry, where we use many different building blocks for organic chemistry, and they're produced on very large scale. Most of these building blocks, or small molecules, maybe 2 to 10 carbons, come from petroleum, and from petroleum we can directly obtain ethylene and propylene. These small 2-carbon and 3-carbon precursors are critical for the chemical industry, and they go on to make a large number of the other molecules that we use. So for example, you can see here ethylene can be converted into many different 2-carbon molecules, including ethanol, acetic acid or vinegar, ethylene glycol or antifreeze. It can be polymerized into PVC, and propylene has a large variety of chemicals that it can be converted to as well. So we should begin this chapter by really comparing addition reactions to elimination reactions. The two go hand in hand, and there's an equilibrium between the two that's dependent on temperature. So we're going to return to the Gibbs free energy equation, and we're going to look at both the enthalpy term and the entropy term. Remember, if we increase the temperature, that means we're going to increase the entropy term. So keep this in mind as we go over the next few slides. In an addition reaction, we're going to be breaking one pi bond and one sigma bond, and we're going to be forming two sigma bonds. Now, sigma bonds are generally stronger and more stable than pi bonds, so overall, this is going to be enthalpy favored. We're going to have a net release in energy and a more stable molecule by an addition reaction occurring. When we look at the entropy term, we're going from two molecules to one molecule. So we're going to have a decrease in entropy, and this will not be favored entropically. So really, the determining factor, if an addition reaction or an elimination reaction will occur, or which side of the equilibrium will be favored, is dependent on the temperature. At low temperatures, addition reactions will be favored, or the right side of the equilibrium, as we see it here. And at high temperatures, it'll go in the opposite direction, where the elimination is favored. The first reaction that we're going to look at is hydrohalogenation. So this is a simple addition of a hydrogen bonded to a halogen over an alkene. Depending if we have a symmetrical or unsymmetrical alkene, there are two potential products. Right here on a symmetrical alkene, there's only one potential product. The bromine, no matter which side of the bond it goes to, is going to create the same molecule. But on this molecule here, we have two potential products. If we put the halogen in this position, it'll be a tertiary halogen. If we put the halogen on this position, it will be a secondary halogen. So this regiochemistry is one of the first factors that we have to look at when we are analyzing our hydrohalogenation reaction. So in 1869, Markovnikov observed that hydrogen atoms tend to add to the carbon that's already bearing more hydrogen atoms. So in a normal addition reaction, the halogen is going to be installed on the more substituted carbon, and the hydrogen is going to be installed on the less substituted hydrogen. So this would be called Markovnikov addition. This is the typical regioselectivity, or the expected outcome for an addition reaction. However, if we use a peroxide, so if we add an additional reagent to the reaction, we can observe the opposite regioselectivity. In this case, we can observe the halogen attaching to the less substituted carbon, and the hydrogen attaching to the more substituted carbon. So because we're getting a different product based on the presence of peroxide, it must be a different mechanism that the reaction is undergoing. And we're going to look at both of these mechanisms, one in this chapter and and we'll look at this specific peroxide mechanism in the future when we learn more about this type of mechanism. But for now, if you have a double bond, we can do an addition reaction of a hydrogen attached to a halogen in the presence of just the hydrogen and the halogen. We're going to get Markovnikov addition, where the halogen attaches to the more substituted carbon. If peroxide is added, then we're going to have the halogen attached to the less substituted carbon. So these are two new reactions that you should be familiar with. We can now convert alkenes to alkyl bromides, or any alkyl halide, really. Let's take a look at the mechanism for this reaction. So the first step of the mechanism is going to be nucleophilic attack, or protonation of the double bond by the acidic proton. So HBr is a strong acid, and so the alkene is going to be protonated to form a carbocation intermediate. This carbocation intermediate is going to form at the more stable position, right? And a more substituted carbon is going to be the more stable position to hold a carbocation. Then the second step of the reaction mechanism is the bromide ion functioning as a nucleophile and attacking the carbocation intermediate. So we're breaking one bond, we're breaking a carbon-carbon pi bond, and we're breaking two bonds. We're also breaking a hydrogen bromide sigma bond, and we're forming two new bonds. We're forming a carbon-hydrogen sigma bond and a bromine-carbon sigma bond. And remember, this is an equilibrium reaction. This is the exact opposite of an elimination reaction. taking a look at the reaction coordinate diagram, we can see that the step with the highest activation energy is the proton transfer step. Then we obtain a carbocation intermediate, which can then go nucleophilic attack. So we have um, two transition states for this reaction, and we have one intermediate. Now there are two potential pathways for this reaction to occur. The anti-Markovnikov pathway is going to have an intermediate with a secondary carbocation, and the Markovnikov pathway is going to have access to a tertiary carbocation intermediate. Remember, if we have a secondary carbocation, what is it going to do first, right? It can undergo nucleophilic attack, it can rearrange. Now we're adding a third thing. It can also do an addition reaction, right? So carbocations can do three things: rearrange, undergo nucleophilic attack, or they can do an addition reaction. And in this case, um, the ability to rearrange always, well, a general rule, the ability to rearrange is always going to occur if there's a more stable position nearby. So the secondary carbocation intermediate would rapidly rearrange to a tertiary carbocation intermediate. And so we'll always have, under these conditions, the Markovnikov product form because of this carbocation stability. The activation energy required to get to the transition state to form a tertiary carbocation relative to a secondary carbocation is going to be lower. So the Markovnikov product is going to form through a lower energy transition state and require less potential energy to reach its transition state. In some cases, we might obtain a chiral center from an addition reaction. Here's an example where that would be true. When we form the new carbon-chlorine bond, we're going to form a new chiral center. So in this case, we'll have a mixture, a racemic mixture, a 50-50 mixture of the two enantiomers, and these two enantiomers will be formed in equal amounts. If we look at the orbital diagram, we can see that once the carbocation is formed, that the carbocation intermediate can be attacked from either side with equal probability. So the nucleophile can approach the p orbital from either angle. And so we'll get a mixture of enantiomers. So just in summary for the hydrohalogenation reaction, remember that we can control the regioselectivity by adding or not including peroxide to get the Markovnikov addition at the more substituted carbon, or to get the anti-Markovnikov addition. Recall that if the carbocation has an ability to rearrange, then the rearrangement will occur. So if we're looking at an addition reaction for this substrate here, after the protonation step, a secondary carbocation is produced. This secondary carbocation then has the ability to rearrange to a tertiary carbocation before the nucleophilic attack occurs. For this specific molecule, we'll see a combination of the Markovnikov addition as well as the addition for rearrangement. The next reaction we're going to look at is the acid-catalyzed hydration reaction. In this reaction, we're going to add the components of water across the pi bond. This reaction will follow the Markovnikov regioselectivity, so we'll have the hydroxyl group adding to the more substituted carbon. Typically, sulfuric acid will be used as the catalyst for this reaction. The more substituted the carbon is, the faster this reaction will occur. And this is because the carbocation intermediate will be lower in energy. And so this data on the relative rate is consistent with the mechanism that we observe for this reaction. And you can see for a um, tetrasubstituted carbon at this point, we have 10 to the 11th reaction rate relative to just ethylene. We're going to have essentially the same mechanism for all of these addition reactions with slight variations. The mechanism for the acid-catalyzed hydration is going to begin with a proton transfer to the Lewis basic pi bond, which will generate a carbocation. The carbocation can then be trapped through nucleophilic attack with water. And remember, whenever we have nucleophilic attack and the nucleophile is a neutral species, we'll generally need to deprotonate with the proton transfer at end to liberate the product. Just like we can control the equilibrium of addition reactions for hydrohalogenation using temperature, we can use the concentration of water to help guide the equilibrium for this reaction. So if we're interested in synthesizing an alcohol from an alkene and we use excess water, it will dilute the sulfuric acid and the equilibrium will shift to the right. If we're interested in synthesizing an alkene from an alcohol, we would use concentrated acid, and this would shift the equilibrium towards the alkene from the left. An improvement upon the Markovnikov acid-catalyzed hydration is the oxymercuration-demercuration. This prevents any rearrangements from occurring. The hydroboration-oxidation reaction is also going to be stereoselective. Because of the mechanism in this reaction, which we'll look at a little bit later, the hydrogen and the oxygen are going to be added onto the same side of a double bond. This is important when we're looking at non-symmetrical alkenes, and especially alkenes that are part of a ring system. We will not observe any anti-addition where the hydrogen and the hydroxyl group would be on opposite sides of the double bond. The geometry and hybridization of BH3 is very similar to that of a carbocation. As you can see here, we have a 120-degree bond angle with all three hydrogens planar to each other, and then two orthogonal or perpendicular p orbital, or one p orbital that's perpendicular to the sigma bonds. Since boron does not generally have a full octet, we're going to generally have a complex of two borons together. So really, it's B2H6 is generally the active species when it comes to boron, and this allows the boron to have full octets when it has this kind of hybrid species. The p orbital of the boron can be stabilized with the lone pair of the oxygen on the THF solvent. So the active reagent for this reaction is going to be a complex of BH3 and THF. Using the hydroboration oxidation, we're going to obtain anti-Markovnikov regioselectivity. The less substituted carbon is going to begin in the mechanism by attacking the boron. Then the boron-hydrogen bond will break and will form a new carbon-hydrogen bond. So this allows us to have the boron attached to the less substituted position and form a new carbon-hydrogen bond at the more substituted position. When we react three equivalents of the alkene with boron, will convert the boron into a trialkyl borane. So this reaction that occurs here is going to occur 3 times until all of the hydrogens are removed from the boron, and we'll have a trialkyl borane. Since the intermediate is going to build up partial positive charge, we're going to want that to occur on the more substituted position, because the more substituted carbon will be better at stabilizing this positive charge. Sterics is also going to play an important role in the regioselectivity. Not only does the more substituted position stabilize the positive charge more, but if the boron were to try to coordinate to that position, there will be some steric interactions between the alkyl groups attached and the boron itself. So this is going to lead us towards a transition state for anti-Markovnikov addition using the Hydroboration-Oxidation Mechanism. And we can draw out the second part of the mechanism. We have a molecule of hydrogen peroxide. It's going to, in the presence of base, form this hydroperoxide, and that will attack our alkyl borane. One of the R groups on the alkyl borane is going to migrate to form a new bond with the oxygen, which then breaks the oxygen-oxygen bond in a rearrangement. And this is going to form the oxygen-boron bond, which can then be liberated through attack of a hydroxyl group, nucleophilic attack, and then the boron-oxygen bond breaks. A proton transfer will finish off the mechanism to produce the alcohol product. So this is a fairly complicated mechanism. There are 1, 2, 3, 4, 5, 6 steps to it, and that's only the second half of the mechanism after the trialkyl borane is produced. Hydroboration is stereospecific, so because of the approach on that face of the alkyl borane, only syn addition will occur. We'll only form syn addition, and the hydrogen and the oxygen will only attack from the same face of the molecule. If we're forming a chiral center, we'll obtain a pair of enantiomers as well, because of the ability to attack from either face. In some cases, we might actually form 2 new chiral centers, and if this is the case, we'll form also a pair of enantiomers because of the syn addition of this reaction. So you can take a moment to pause the video and practice this problem. Try to identify the products that will form from this reaction.